CNBC-TV18 and Intel present Business Comes Alive, Intelligence Everywhere. We will now have the opening keynote, 6 Pillars of Technology, powering Intel's leadership product roadmap. To deliver the keynote, please welcome Raja Koduri, Senior Vice President, Chief Architect and General Manager, Architecture, Graphics and Software, Intel Corp., and Wei Li, Vice President, Chief Architect for Machine Learning Software and General Manager, Machine Learning Performance, Intel Corp. Welcome to the event, Raja.
I hope everyone is doing well and staying safe. We are in the midst of a worldwide pandemic, which is impacting many lives and many more livelihoods. It is interesting to take a moment and reflect on the role of technology in our lives during this time. It's no longer a nice to have. It's a necessary ingredient in our lives now, and AI is playing an increasingly important part of everything around us. AI has touched many elements of our lives, from how we use the internet, connect and communicate with others, to changing industries from agriculture to healthcare. As technology architects, Wei and I think a lot about future trends and how to chart pathways to solving bold challenges. In our talk, we'll touch on a few topics, from industry trends to our approach to delivering ever more AI performance, and to Intel's comprehensive portfolio of AI products. First, let me take a moment and reflect on the past few decades. In the last 40 years, we have seen some amazing technology-led disruptions when we made a lot of performance available to a lot of people. The key is a lot of performance to a lot of people. In the PC era, we digitized everything we could and networked everything we could. In the end, we got 1 billion people onto the internet, and it changed the way we learned and worked and entertained ourselves. The next disruption was the mobile plus cloud era, which connected 10 billion mobile devices to supercomputers in the cloud. And this changed the way we live. What's the next disruption going to enable? I know I'm getting into the dangerous game of predicting future here, but let me share with you the future I am excited about. 100 billion devices that are connected and intelligent, protecting and enriching our lives in more ways than you can imagine. Intelligence will require a ton of computing, exascale and beyond, computing that should be equally accessible to anyone and everyone, computing that can access and address data that can reside anywhere in the world, computing that's not just controlled by a few and not controlled by proprietary abstractions and service layers. Exascale computing should be as accessible to everyone as electricity is today. This is the future that excites me, and I believe should excite all of you as well. This is a 10x growth opportunity for the whole industry. Okay, time for reality check. As I noted, intelligence requires a ton of computing. Our pursuit and advances in AI have resulted in compute need that is at a much steeper trajectory than Moore's law, the exponential trajectory that helped us with the disruption so far. I know this chart is a very familiar chart for many. I won't dwell on it too long, but the key call-out is the staggering demand for compute, doubling every 3 to 4 months in our pursuit of intelligence. Now, there is another thing about intelligence that makes it even harder. It needs both performance and generality. While I wouldn't take the numbers on this chart too literally, the key call-out in this chart is constrained world versus unconstrained world, and fixed function versus general purpose. So what makes our pursuit of intelligence super hard is that not only do we need more compute at a faster pace than we have ever had, we also need it to be general purpose. And if you are already overwhelmed on how hard it is, wait for a minute. We are making it even harder. One of the key breakthroughs in our progress on AI is data, leveraging data to build our intelligence. But as a world, we are generating a ton of data every second. We are generating more data than our ability to analyze and understand. Data not only stresses the need for more compute, it stresses our whole infrastructure. We need more capacity and bandwidth at every level of the memory hierarchy. We need our network bandwidth to go up on exponential trajectories while reducing latencies as well. The question is, how do we go about solving these exponentially hard problems? Moore's law has been the exponential technology entitlement for the whole industry or the last 2 eras in computing. But in the new intelligent era, the path of extracting exponential value from transistor technology requires a whole new approach across the whole stack. This led us to what we at Intel called our 6 technology pillars. Advances across all these pillars are necessary to continue the essence of Moore's law, which in its golden age led to doubling of user experience every 18 months. We said we will deliver a diverse mix of scalar vector matrix and spatial architectures designed with state-of-the-art process and packaging technology, fed by disruptive memory hierarchies, deployed at hyperscale with light-speed interconnect links, unified by a single software abstraction with benchmark-defining security features. We've been working hard on accelerating this vision, and today we will share progress on our AI hardware and software. Let me hand it over to Wei.
Thank you, Raja. With a combination of strong hardware and software, we can enable all of you to deploy AI everywhere. Let's start with an example of AI everywhere. I travel around the world a lot. One thing I noticed everywhere is the popularity of burgers. Even during the pandemic, we can't live without a burger. A few weeks ago, my kids wanted to get a takeout, so they ordered burgers for our family. Early this year, I read some news in Japan about increasing competition between 2 fast food rivals in Tokyo. If you are the CIO for a fast food chain, you must also be thinking about how to use AI to improve customer satisfaction and increase sales. You may think one has to get a supercomputer and build a research team of data science PhDs to do this. I would like to tell you that you don't have to do any of that, because we can provide the AI infrastructure with a rich hardware portfolio and unified software. If AI can be used for burgers, then AI can be used everywhere. Let's look at a few trends in AI. The first trend is about AI models. AI is getting smarter and smarter. It is usually done by making the models bigger and bigger. For example, in the field of natural language processing, just 2 years ago, an AI model like Elmo had 94 million parameters. Then last year, BERT came along with 340 million parameters. You may have noticed there are Sesame Street fans here. Just a few months ago, OpenAI announced GPT-3. It contains 175 billion parameters and is growing exponentially. Also, there's an effort to run AI workloads more efficiently so we can enjoy AI in low-power devices such as a watch or a camera. The second trend is that the field of AI is evolving rapidly. The breakthrough in AI first focused on solving computer vision use cases. If you look at the first pie chart, more than 90% of the time was spent on matrix multiplication. Now, AI covers many more use cases, such as natural language processing and recommendation systems. If you look at the middle and right pie charts, we are still seeing a good portion of matrix multiplication, but they also include a diverse set of other operations. The third trend is there's a great need for end-to-end AI pipelines. Our customers have a lot of data. Each of them has their own AI data pipelines. They have to ingest data, pre-process by feature engineering, sometimes using machine learning, train the model using deep learning or machine learning, then deploy the model. So our customers need machine learning, big data analytics, and deep learning all working together to solve their problems. Because of the versatility of Xeon processors, AI pipelines today largely run on Xeon, particularly in the production environment. Our AI infrastructure will be built on top of both hardware and software. Now, let me show you our hardware portfolio first. In 2018, we laid out the notion of scalar, vector, matrix, and spatial architectures based on the ever-increasing diversity of workload patterns running on our CPUs. Our strategy is not to deal with each of these heterogeneous architectures separately, but to solve problems holistically as one XPU architecture with a single software abstraction. The goal is to move from CPU-centric to XPU-centric computing as the diversity of workloads increases. The CPU's scalar architecture and general-purpose computing capability has made it widely adopted from PCs to data centers around the world. Over several generations of products, we have added features improving AI performance, from the support of new data types to new heterogeneous instruction extensions, while leveraging the general-purpose computing capability of the scalar architecture. As example, vector neural network instruction, or VNNI, was added to Cascade Lake to speed up the computation for convolutional neural networks and led to a significant performance gains. In fact, with the explosion in demand for AI acceleration, we continue to add more heterogeneity in our CPUs, including the bflow16 data type in Cooper Lake and advanced matrix extensions, AMX, in our next-generation Sapphire Rapids CPU. With extensions like VNNI, AMX, and support for formats like bflow16, the heterogeneous ops for AI in CPUs keeps increasing at a pretty steep rate. If you play hockey, you may recognize the hockey stick here. Now, GPUs are a general-purpose architecture as well that can solve graphics, media, AI, and scientific computing problems very efficiently. In 2018, we lay out our XE strategy, a single XE GPU architecture which can scale from teraflops to petaflops, and we're executing on that strategy. We also added many extensions to our XE GPUs to accelerate AI workloads as well, which includes XE matrix extensions, XAMX, and new data types like bflow16. Intel has more than 20 years of experience in integrated GPU design, which reach hundreds of millions of users every year. We have built a rich set of drivers and support for various APIs across all the key operating systems. We have a very broad and deep software ecosystem for CPUs as well. The Xeon and integrated GPU software foundation allows us to build a single GPU architecture which cover multiple market segments with many price points and performance levels. Our strategy is playing out with the launch of our first XE-LP GPU in the latest 11th Gen Intel Core processor. The new integrated XE GPU is delivering up to 5x better AI performance with DL Boost. We have also delivered DG1, Intel's first discrete GPU in more than 20 years, based on the same XE-LP. Our first XE HP silicon has been back in the labs for a while now. It has successfully powered on. XE HP will bring petaflop scale computing on a single package that is deployable at the edge and cloud. Petaflop is a big number with 15 zeros. We have such a comprehensive AI portfolio, ranging from general purpose to purpose-built products. Nearly every product we have developed has packed more AI features and performance than ever before. For advanced spatial architectures, we have a line of FPGA products optimized for AI, with the launch of the Stratix 10 NX FPGA. For improved efficiency, a range of purpose-built solutions are available, from Movidius VPUs, which accelerate computer vision and AI at the edge, to Habana's Gaudi and Goya processors for AI training and inference in the data center and cloud. The key question is, what is the software infrastructure to enable the performance for this rich set of XPU architectures? Now we have the three AI trends at the top and the rich AI hardware portfolio at the bottom. In the middle, it is where AI software comes in. We're building a broad software ecosystem with a two-pronged strategy. This is critical for end-to-end AI pipelines. We want everyone to use the software they're familiar with, including deep learning, machine learning, and big data. If you have recently graduated from a prestigious university in Singapore, Sydney, or Jakarta, you may have learned TensorFlow, PyTorch, or XGBoost. If your company has a data center, you may have used Spark already. We have heavily optimized these frameworks and libraries to run well on Intel platforms. When there's a gap, we develop our own software, such as OpenVINO, which is designed for deep learning inference for multiple architectures. The important part here is to scale AI software across CPU, GPU, and other XPUs. You can imagine the number of combinations will be very large. One API will provide that scalability. I will come back to one API later in this talk. We have also created solutions like Analytics Zoo for data scientists. Analytics Zoo is an Intel open source project that makes it easy for people to develop and deploy AI models. Software can make a huge performance difference for AI. Let me show you an example on Xeon. When deep learning started several years ago, the open source software was not optimized for CPUs. So there was a huge opportunity to make a huge difference. My team stepped up to optimize the popular libraries and frameworks. We have dramatically increased performance for both training and inference on Xeon. We were able to improve performance by 285x on the Skylake platform through software optimizations. 285x is a very meaningful improvement. Since then, we continue to add hardware AI features and software optimizations. We managed to reduce inference latency from seconds to milliseconds to achieve real-time AI inference for our customers. That's why they're running most of their deep learning inference on Intel CPUs today. And we also reduced training time from weeks and days to just hours and minutes. Customers benefit from this the most. We have seen a wide range of customers, from cloud service providers to healthcare and financial industries. There are many reasons customers choose CPUs for AI. CPUs are broadly deployed and available. CPU is where the data resides. And the CPU is general purpose that can run any application. Let me show you another recent example. Last year, Facebook released DLRM, a recommendation workload. we were able to boost the training performance of DLRM on a single socket by 7.8x with just software optimizations. With additional optimizations for distributed computing using our 1CCL communications library, we were able to achieve a whopping 133x performance boost. Now let's see how software can use hardware AI features to improve performance. bflow16 is a new data type recently introduced in the AI community. It has half the number of bits as FP32, but the same number of exponent bits to keep the dynamic range of data. It can achieve better performance than FP32 without visible loss of accuracy and improve energy efficiency. Let's look at a demo of the performance improvements. FP32 is on the left-hand side and bflow16 is on the right-hand side. In the middle, you can see that bflow16 runs about 1.9x faster than FP32 due to doubled peak throughput per cycle. Even with the reduced precision, training results using bflow16 show no loss of accuracy compared to FP32. With this feature on Xeon, we have not only improved performance, maintained accuracy, but we also have improved energy efficiency for AI. I have shared with you what we are working on today. Where does this lead us tomorrow? Our goal is to develop a scalable end-to-end AI infrastructure for XPUs. Both machine learning and big data have been running on Intel for many years, and we continue to optimize the frameworks and libraries. With our recent software optimizations, most deep learning inference and end-to-end AI now also runs on the CPU. You can do training as well on CPUs like Xeon. Going forward, we will expand our software stack to XPUs, which include CPU, GPU, and AI accelerators. If you were to replicate the software stack I just talked about across additional architectures, the stack will look pretty on a slide like this, but it's not practical. We have over 10,000 software developers just for CPU. Hiring 60,000 more for different XPU architectures is not a scalable solution. So what is the solution to this problem? Our answer is One API. One API is a cross-industry, open standards-based, unified programming model across architectures. The One API specification extends existing developer programming models to enable a diverse set of hardware through language, a set of library APIs, and a low-level hardware interface to support cross-architectural programming. At Supercomputing in 2019, we released an early draft of the One API specification and launched our first public beta of One API with support for CPU, integrated GPU, and FPGA. This month saw the release of version 1.0 of the One API specification and our 9th iteration of One API beta, which delivered new features and enhancements for distributed data analytics, rendering performance, profiling, and our video and threading library. Looking ahead to our goal release of One API, we will provide developers with production-quality tools and libraries supporting CPUs, GPUs, and other accelerators. One API Gold will be available to developers later this year. Now let's come back to our favorite fast food example that I mentioned earlier. My team worked with a multinational fast food chain to deploy AI. The goal was to improve the customer experience and sales. A customized recommendation was developed on the mobile app by considering two types of information. The first was guest order behavior, and the second was context information like weather, time, and location. For example, you wouldn't want to offer ice cream during the winter in Alaska around midnight. So how did we do it? First, an AI pipeline was created with data already on the Xeon cluster running Spark. Adopting our analytic zoo minimized the data movement across clusters. Analytic Zoo also integrated MXNet, which was used for a deep learning algorithm based on the transformer architecture. The model was trained and deployed in the mobile application. I tried the application on my phone, and it offered me my favorite French fries. AI is also used in the financial sector. For example, risk assessment for loans. This example shows a customer with a data pipeline experimenting with various machine learning algorithms from linear regression, gradient boosting, random forest to neural networks. Due to the nature of the data, the bottleneck is at the manually intensive data prep stage. As you all know, a data scientist's time is very expensive, so finding a way to optimize this is important. We are developing modem to significantly speed up the data prep stage. This is also running on Xeon. With the rapid advancement of 5G technology, more and more data flows from mobile edge devices to base stations. For example, a major telecommunications company has thousands of cell towers and millions of subscribers. This network must handle billions of records every day. With this massive amount of data, they can effectively predict network quality. The old data pipeline had two disjointed flows, which was not very efficient. The new pipeline with our Analytic Zoo software unified data pipeline and efficiently runs on Xeon using Spark and TensorFlow. We have advanced our AI hardware capabilities not only in data center but also in client. The 11th gen core processor has improved AI significantly with the power of XE-LP GPU, OpenVINO software, and the Intel Gaussian and Neural Accelerator, or GNA. GNA is a low-power neural coprocessor for continuous inference at the edge, like noise reduction and speech recognition to save power and free CPU resources. Not a long time ago, when I had the privilege to travel a lot, I had to call in to meetings from the airport, which is challenging with a lot of background noise. It would have been great to automatically eliminate that distraction. With today's current environment, that background noise removal is even more relevant for the majority of us who are now working from home. Just last week, I had a meeting with someone who had a baby crying in the background. Tiger Lake has made these applications possible. AI is also used for image processing. Let me show you an example on Tiger Lake using DL Boost technology in the XE GPU.
Here's a practical application and results of optimizing AI inferencing on XE-LP. Topaz Labs created a photo enlarging application called Gigapixel AI. This application uses deep learning that can imagine new details in your upscaled images. This produces stunning results that were simply not possible before the use of AI. However, these methods are incredibly math-intensive, requiring trillions of calculations to upscale even a single image, like in this 2x preview. Let's start processing the photo set. Topaz Labs worked with Intel to optimize their AI acceleration, and they did this by integrating the OpenVINO toolkit. OpenVINO leverages the inherent acceleration of int8 inferencing, utilizing the DL Boost DP4A instructions in the new XE-LP graphics. Here, you can see the performance improvement over 3 generations of Intel graphics. It is exponentially faster on XE. Already completing the batch processing, while Gen 11 is partway through and the older 9th Gen is still just starting. AI changes our expectations of what our technology products do for us. Intel continues to innovate both in AI hardware and software architectures to meet this growing demand.
There was a lot of work that went into the AI software to enable developers like Topaz. I have one team working on OpenVINO and another team working on the GPU Deep Neural Network library. They worked with Topaz to accelerate Gigapixel. If you are an ISV, you may be thinking how you can apply AI in your applications using the tools we have developed on our latest hardware. The good news is that we have created the Intel Dev Cloud, which exposes our libraries and toolkits to developers, allowing you to start writing software using one API, even before having hardware in hand. Dev Cloud is very easy to use, requires no hardware installs, no software downloads, and no configuration setups. I'm also super excited to share that our first discrete GPU, DG1, is currently available to early access developers in the Intel Dev Cloud. Through the course of this talk, you heard Raja and I share exciting innovations and products across our XPU hardware and AI software. We also saw examples and demos of how we are solving customer problems with AI across the data center, edge, and client. Intel has a diverse portfolio of hardware ranging from general-purpose CPUs and GPUs to purpose-built AI accelerators. We have a comprehensive software stack covering deep learning, machine learning, and big data analytics optimized for Intel's platforms. With these, we can help you deploy AI everywhere. Thank you for joining us today. We look forward to seeing you all in person next time. Stay safe.
Thank you, Raja and Wei Li, for the detailed session. Our next keynote is Intel AI Strategy Overview. To attend this, please return to the virtual platform's keynote section.